Run your hand across a wooden table, or stare into a glass of water, and it feels like you're interacting with perfectly continuous, unbroken blocks of stuff. But if water is a solid block of liquid, how can you pour a spoonful of solid salt into a full glass, watch it disappear entirely, and not have the water spill over the edge? And if the air around us is just empty space, how does the scent of hot food travel across a room to reach your nose before you even see the plate? These anomalies point to a hidden structure. If water has gaps for salt to fill, and air acts as a highway for invisible scents, then matter cannot be one solid block. It is a collection of individual, distinct particles. The scale of these pieces is nearly impossible to picture. Drop just a few tiny crystals of potassium permanganate into a 1,000-liter tank, and it explodes outward, coloring the entire massive volume of water. Everything we interact with is governed by hidden rules acting on these invisible pieces. To understand how our physical reality takes shape, we have to decode how these particles behave. First rule, particles have empty space between them. Rigid salt crystals break apart and slip into the gaps between water particles. Second rule, particles possess kinetic energy, constantly vibrating and ricocheting. Third rule, attractive forces act as invisible tethers, pulling particles together. These three rules create an active, microscopic tug-of-war. The balance between the outward energy of motion and the inward pull of attraction dictates the physical form of every object on Earth. When the attractive force wins that tug-of-war, we get a solid. The particles still vibrate, but they are locked firmly into a rigid, dense grid. If we increase the kinetic energy, the particles break out of that rigid formation. They stay tethered, but tumble and flow past each other, settling into the shape of whatever container you pour them into, creating a liquid. When the kinetic energy completely overpowers the attractive pull, the tethers snap. The particles go zipping off into the void, expanding rapidly to fill any available space as a gas. Because gases have an immense amount of empty space between their flying particles, we can forcefully squeeze them back together. We harness this by compressing massive volumes of natural gas into tight cylinders to power vehicles. Take solid ice, flowing liquid water, and rising steam. They are the exact same matter, simply exhibiting different behaviors based on how much energy they hold. We force matter to change states by turning two dials, adding heat or manipulating pressure. When you apply heat to a solid, you inject it with kinetic energy. The particles vibrate faster and faster until the attractive bonds snap. This chart plots temperature over time as we apply a flame to ice. Watch the line. It rises steadily, but the moment the ice begins to melt, the temperature flatlines. It stops rising completely, even as we continue blasting it with heat. The heat isn't vanishing. Instead of raising the temperature, this hidden energy, known as latent heat, is being spent entirely on the physical labor of severing the bonds between the particles. Pressure works from the opposite direction. By exerting extreme force, you can squeeze chaotic gas particles so tightly together that they lock into a grid, completely bypassing the liquid phase. We see this process used industrially to create dry ice. By increasing pressure and lowering temperature, carbon dioxide gas deposits straight into smoking, solid blocks. By shifting temperature and pressure, we dictate how particles organize, giving us the power to transform the physical properties of the material world. These microscopic mechanics follow us out of the lab. Every time you feel a breeze or watch a puddle dry, you are witnessing the process of evaporation. If you spill rubbing alcohol on your hand or step outside covered in sweat, your skin instantly feels cold. This cross-section shows liquid on your skin. Below the boiling point, surface particles gain enough kinetic energy to break their tethers and escape as vapor. But this escape takes a toll. Departing particles steal heat energy, pulling warmth right out of your skin.